Hi, my name is Dear Tiagi, and in this video I'll be going over Lagrange Error Bound, which you'll need to know for the AB Calculus BC exam. So to start, when do we use Lagrange Error Bound? Well, we use Lagrange Error Bound when we're when we're finding the maximum possible error for a Taylor approximation. So in other words, let's say we have a Taylor series, and the sum of the Taylor series is S. And we're approximating the sum using an S of n. If we subtract s from S of n and take the absolute value of that, what we get is a remainder R of n. Okay, and this is the remainder from the actual value subtracted from the real value for the approximation. Okay, and so we get a remainder R of n. And so basically, Lagrange error bound tells us what the maximum error is. So the maximum error would have to be, based on Lagrange error bound, it's maximum of the fn plus 1 derivative times x minus c to the power of n plus 1 over n plus 1 factorial. So basically, Lagrange error bound tells us, again, the maximum error. So whatever error we get from the approximation using some value of n, Lagrange error bound tells us that our maximum value is this value. So it can't be anything higher than this. Now, what is this? This is, I'll explain each part separately. So this max fn plus 1 z is telling us we want to find the highest value of the derivative n plus 1 on the interval from x to c. So we're looking for the highest value for the derivative on the interval x to c of the n plus 1 derivative on the interval x to c. Here, x represents the value we approximated, the value we're approximating using our Taylor approximation. C represents the center of our Taylor series. And again, n just represents the degree, our original degree of our Taylor series, the degree we're estimating with. So degree estimating Taylor series with. And again, if you recognize this, you might see like, oh, this is just the same thing as the formula for a coefficient in the Taylor series, or for a term in the Taylor series, because this is just f of n of c, of a times x minus, of c times x minus c of n over n plus 1 factorial. So it's the same thing as that, except we just add n plus 1 and we're finding the max derivative. So it might seem complicated, but it really isn't. Let's try out a couple examples. So for the first example, let's say that we're trying to find the max error in approximating sine of 1 using a fifth degree Maclaurin series. And we're asked to find the maximum error. So the error is equal to, max error is equal to the Lagrange, the absolute value of Lagrange, which is equal to, and now we want to find out these values so we can use Lagrange. So first, we want to find the max value of f of 6, the sixth derivative, at any value z on the interval 0 to 1. So in this case, what happens with sine, so we have sine, it becomes cosine, sine, cosine, sine, cosine, cosine, and it goes to that. So we can write it on the side. So sine, this is our 0th derivative. Cosine is the first derivative. Then we get negative sine, second derivative. Then we get negative cosine. Sine, So we have first derivative, second derivative, third derivative, fourth derivative. Fifth derivative is cosine, and then sixth derivative is negative sine. Wait, first, second, third, fourth, fifth, sixth. So yeah, that's the derivative there. And now we want to find the max value. Actually, we didn't have to do this. Think about it. We sine and cosine. The max value on the range 0 to 1 of any derivative has to be 1. Because again, if you think about sine and cosine, sine has a maximum at pi over 2, and cosine has a maximum at 0. And this is in the interval 0 to 1. Therefore, any value, the max has to be 1, no matter what value we choose, or ends up on. So we have 1 times x minus c. So x is 1. That's the value we're approximating. And the c, it's Maclaurin series, so the c is 0. So times 1 minus 0 to the 6th power over n plus 1 factorial, so 6 factorial. So our final answer for the error is 1 over 6 factorial. So again, the process is we use the Lagrange formula, we find the max. In this case, the max was easy to find. We'd have to use this chart I made, because the max on the interval 0 to 1 of the sine function, no matter how many derivatives we take, because it's cyclical, it has to be 1. And then we just plugged all the other numbers in, and we got our answer. Let's just try one more. Let's say we have, let's say we're doing the function, we're trying to find the max error in approximating e using the fourth Maclaurin series for e to the x. So in this case, let's do the same thing. Let's identify what we know. So we know that the max f of, so n is 4 in this case, the max fifth derivative on the interval, and we're doing, again, let's do c, center is 0, it's Maclaurin series, and then x is 1, because again, we're estimating e, and so we're doing e to the power of 1, so we're using e. And so the maximum error number on 0 to 1, or sorry, the maximum derivative value on 0 to 1 has to be just e, because again, if you think about the derivative of e to the x, you get e to the x, e to the x, e to the x, so it keeps going like that. So the max value for the derivative is e. Now we can just plug into the Lagrange. We get r of n is equal to the absolute value of the max, which is e, times 1 minus 0 to the 5th power over 5 factorial. And so our final answer is e over 5 factorial. So these problems are really simple once you know the formula. All you just need to remember is how to find the max derivative, which is usually easy. Usually you can figure out like pretty easily if it's cyclical or if it's like this, or they give it to you straight out in the problem. And then you just plug in the numbers xc and n plus 1 and all that. And you'll get a max possible error. And yeah, that's it. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.